All right. Sorry, I'm all clogged up. Start from the current slide. Even turn the projector on. Let's go over just quickly what's about now that I'm recording, so others who aren't here will hear too. I've received 2 of the 3 papers, yours included, so thank you. Gotten the research papers in for 2 out of 3 of you. Only got 1 of the first test in. That's yours. Thank you very much. Okay. Second test, I don't have any of those in. Still working on that? Huh? Oh, you didn't get one? My goodness, I wish you'd have said something sooner. Okay. Second test. Test 1. Test 1. Test 1. Test 1. Test 2. I don't think that's ours, is it? Hey.
Can I have another quiz?
Pardon me?
I misplaced my quiz.
I'm sorry.
Quiz for this morning?
Yeah, what about it?
Misplaced.
Okay, well, I don't have it up here with me. It's down in my office.
I don't know what I did. Hopefully it's in the car. I don't want to have to come back up.
Okay. How long are you going to be here?
It's at 3:30.
3:30. Okay, I'll be getting out of this class at 1:55. So I can, if you'll come back up right at 1:55, I can run.
I'll go see if it's in the car.
Okay. Yeah, because I'm in class right now.
Okay.
Yeah, small class. Okay. 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 Trying to think. I have several copies of your test 2. I guess this is it. Okay. Let me remind myself that was chapter 13, right? Yeah, vector value functions. I think this is it. See if that looks familiar to you. They only want to have a spare copy right now on test 2. So I think that look reasonable? Okay. Sorry, I didn't know you didn't have that. Okay. So, like I was saying, I haven't gotten test 2 back from anybody, and we're in chapter 13 now, and wait a minute. That is, that's why, okay, I haven't passed it out yet. I was looking at Cal 2. That's why. Yeah. It looks like we're only going to have the 2 tests this time, which is not what my design or plan was, but so let me put this back in. Yeah, that will be the final. You've just seen it. Okay. I assume it will. It may have some different questions on it. Because I was going to say, I'd made 10 copies of that. I said, I don't have 10 people in this class, so why do I have 10 copies of that? That was from the summer, and I had a big class. All right, so when we finish this chapter, that's what the last test will be, and that will be similar to what you just saw briefly. Okay. All right. Okay. All right, that's done. So, we're going to continue in chapter 13, and I'm trying to see where okay. For some reason I turned back. We're in 13.5, I'm pretty sure. Nope. Goodness gracious. I have the figure where we are. I just, for some reason, I've turned off the right page. We're past this. How did I do that? Motion in free space. No. No, wait. I know, I turned back because of that. Okay. I had the pen in the right place. Sorry about that. Okay. My head's not on right. All right, we'll finish chapter 14. 13 is one you've already been tested over. With end of 12 and 13. That was your first test. And we're almost through with 14.5. We're going to finish that real soon. And that finishes chapter 14. Then I'll give you that test. Okay, that's what it was. And then no, I'm sorry. That finishes 14.5. Then we'll move into 14.6, the chain rule, and 14.7. We're not going to do 14.7. And 14.8. And then we'll start at 15. Okay, so yeah, we don't have that much more to go in chapter 14. Where we are. All right, what I want to do next time is return and this is not necessarily for you because you've turned in everything. I need to return your first test to you. This is for the other people who aren't here, and therefore you have to have those in to me before class on Wednesday. Okay? Now, that's right where I was going with this. So please get me your first test, and I'll be giving you your second test probably at the end of the day today. And then we're going to cover what we can in chapter 15. I want you to be exposed to that. And I might throw in a couple of extra questions just to make it easy for you. Yeah, okay. All right, good deal. Other things. Have you done the student course evaluation? Yes, good. Others of you, please do that. All right. And what's next Tuesday? Not tomorrow, but next. The election for the senator. Please don't forget to vote. Okay, that's not has to do with math, and it is during finals week. You're absolutely right. Okay, and let's see what else. I think that's all. Okay, so we're at on page 782. This is chapter 14, differentiation in several variables, 14.5, which is gradient and directional derivatives. Example 11, the bottom of page 782, moving on to the top of 783. Any questions before we get going on it? What's that? What section? 14.5. Gradient and directional derivatives. And here's example 11. Sorry, I can't clear my throat. Okay, here is the figure that we're talking about. Here is an illustration of a mountain, let's say, and you're in the process of wanting to climb the mountain. And what we do, we imagine the mountain up here somewhere, and we imagine a domain down here, okay? Now the domain down here is the XY plane. The vertical part is the Z, okay, going upward. So if your surrounding landscape was at 0, you set this down, but it would be hard to see this, so they sort of elevated it up there. And what we have here is you're standing on the side of a mountain, I think at position Q, and the mountain has a shape of Z is equal to f of xy. You see up near the top there, Z is equal to f of xy, some function of x and y. X and y describing your base, the the plateau at the bottom, okay? And you're at the point Q. Yeah, that's where I thought you were. Just above P on the XY plane is the point Q on the mountainside. And this has components, A on the x-axis, B on the y-axis, and then alpha of AB would be your Z component. Okay? So AB, alpha of AB. Now, the gradient F at AB, remember that's just a scalar function. Z is equal to alpha of xy. Okay? The gradient is the slope, the maximum slope up the mountain at that point Q. Okay? Because you're at the point AB. And they tell you the gradient is 0.4, 0.02. Okay? Now they haven't told you that here, so let me shrink this down. And let me get my pen activated. Something interesting has happened. You've been in my class before. Before, I couldn't pick out this letter here because this symbol was over on top of it. And something happened today that it has it scooted over here, so I can choose black. I've been having to choose a very dark purple because if I had tried to choose this, it would turn it off. Okay, so now I can choose that. And I don't know what has changed, but something changed over the weekend, so thank goodness. Okay, not that it mattered. Okay, and they tell us here that the delta, that the gradient of F at AB is 0.4, 0.02. Okay, so that's what's represented here. The gradient, goodness gracious, I can't write, of F at AB, that's all they tell us, this point right down here. This is A, and this is B. Okay, so that point here is AB, and this Q is at point A, B, alpha of AB. Okay. All right. So the gradient of F, and that's a vector quantity, at the point AB is the vector that is 0.4, 0.02. 0.4, 0.02. Now, that doesn't seem like a very steep gradient there. The picture looks like it's a lot steeper than that, but it's 0.4 in the x direction, which frankly doesn't look at all correct. Okay? It would look like to me that it's going up in Z when it's going backward in X, because it looks like to me this is pointing more that way, toward the top of the mountain. Now, maybe I'm wrong on it, but then the Y direction, there's, very little. In fact, it looks like they've got the components backwards. Looks like you got a huge gradient, a larger gradient in Y than you do in X, okay? Because it looks like in X, you're going slightly back in X when you're going up the mountain, and here you're going considerably forward in Y when you're going up the mountain. So I don't see that their numbers here are matching their figure very well at all, okay? Sorry about that, but the figure is just representative. It doesn't have to do anything. Okay, it says find the angle of inclination in a direction making the angle theta is equal to pi thirds with the gradient. Okay. Now this was the conceptual insight we had just before we quit last time. Okay. So let me write down what that conceptual insight was just above example 11. This was that the tangent of the angle psi, they pronounced it a weird way, psi or something like that, is equal to the directional derivative in the direction of u, and that's usually a unit vector u, f at p, okay, where p is this point right down here. Okay? The steepest gradient up the mountain is in the direction for which the horizontal displacement is in the direction of del FP. Well, okay, sorry about this. They are using a different symbol here. In the conceptual insight, they were using psi, they say, or psi. So the problem here, find the angle of inclination. Okay. In the direction, find the angle of inclination in a direction making an angle theta equals. So yeah, theta is different. That's pi thirds. Okay. So the gradient is this way. Okay. And this psi is going to be, that's what we're looking for, but the theta here is the angle of inclination in the direction making an angle of theta equal pi thirds with the gradient. So the gradient is this up the hill here. That's the gradient, steepest approach. Psi is the angle that it's making with u, okay? And u is making that again, I don't really like the way they're drawing this, okay? It's really hard to see is one thing, but the other, the angle of inclination, where they've drawn this, that doesn't look like an angle of inclination, okay? Directional derivative is related to the angle of inclination in figure 12, which is, yeah, this picture we have here. Think of the graph of Z. Oh, wait. Sorry. No wonder this is making no sense. Sorry. This graph here, figure 12, is referring to that conceptual insight. Okay? It has nothing to do with example 11. Because it follows example 11, I was saying they're trying to make this do. Sorry about that. Wrong answer. Okay? This is the figure that went with conceptual insight. That's what they're showing there. Example 11, no wonder this didn't make a lot of sense. So, all right. All right. Yeah, sorry about that. Okay. Now, you're standing on the side of a mountain in the shape z is equal f of xy. So you can almost imagine that picture. It's just not the right picture. At a point Q, and the point Q, AB, that's why they didn't show AB on here, f of AB, where the gradient is 0.4, 0.02. That gradient is nowhere close to this one, okay? So that's what we know. And let's separate this. In fact, I'm just going to erase all that. Okay. Now, the gradient of f may have nothing to do with that picture. At AB, and you can sort of look at the picture and see if it's making some sense to you. This is 0.4, 0.02. 0.4, 0.02. Okay. That's why that picture was making no sense, because it has nothing to do with this one. It says find the angle of inclination in a direction making an angle of theta equal pi thirds with the gradient. Okay? Now, let's go back to your directional derivative here. Let's do a couple of pieces here. First, here is a tangent of psi. That is your angle of inclination. That's what we're going to be looking for. This is our unknown here. Find the angle of inclination. Okay? And the definition from your conceptual insight is that this is your directional derivative in the direction of u, f of p. Okay? Now, if you turn back one page, Theorem 4 tells you what that is. Okay? That is the magnitude of your gradient vector, f sub p, okay, times the cosine of the angle theta. And your angle theta here is that pi thirds. Okay. So the picture doesn't have much to do with this, except that was illustrating where we got that tangent psi formula there. Okay. Now, we can do this now. What we need to do is, first, of course, get the magnitude, the magnitude of your gradient vector. We know what the gradient vector is. So it's magnitude, and f of p, f of ab, that means the same thing. Okay? And what is if you know the components, what's the magnitude? 0.4 squared plus squared, and that would be the square root of 0.16 plus 0.0004. Have to 4 decimals there, right? So this is going to be the square root of 0.1604. Not going to be a lot different from 0.4, but see what you get. 0.42. Okay.
It's 0.1, the square root of 0.1604.
Yeah.
I got, in my calculator, I got
0.400? I think it's supposed to be 0.42. Let's see what they got in the book. They just do 0.4. Okay, so pretty close. I think it's supposed to be 0.42, but they just rounded to 0.4, which basically it's all in the x direction. Okay, so if u is a unit vector making an angle of theta equal pi thirds with that, then your tangent of psi, that's what we're looking for, is equal to 0.4 times cosine of pi thirds. You know what cosine of pi thirds is? One half. I think you do know that. Okay. All right. So this would be 0.2. Okay. 0.2. Okay. And tangent of psi is equal to 0.2, so take the inverse tangent of that. So psi is equal to inverse tangent of 0.2. 2. I say 2 and write a 4. Okay. And what do you get that to be? Okay, 0.197 radians. And if you wanted that in degrees, you have a degree conversion on that. Yeah, that's what they got, 11.3 degrees. Okay. So, don't worry about the picture. That was what was driving me nuts. I said, this isn't drawn right, okay? But the picture was from the conceptual insight, not from this thing. So that's what it was.
And this problem you were looking for
Side. They didn't say in degrees, so it just said, you're standing on the side of a mountain in the shape blah, 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 at a point blah, blah, blah. Find the angle of inclination in a direction making an angle of theta equal pi thirds with the gradient. So that's what you were looking for, and you could put it either in radians or in degrees. They just showed you both. All right. Now, another use of the gradient is in finding normal vectors on the surface with an equation alpha of x, y, z equal k, some constant, and here's the theorem that goes along with that. Okay? It's not quite the theorem yet, but it's close to it. The key to their wording there is finding normal vectors on a surface with an equation that function is equal to a constant. Well, if it's equal to a constant, its derivative is 0. Okay? So if you do the partial of alpha with respect to x times the change of x, plus the partial of y with respect to y times the change of y, plus the partial of y with respect alpha with respect to z times the change of z, and take the derivative of a constant, which is 0, this is the formula you get. Okay? And that's the gradient as a normal vector is what they are labeling this as. Let P be some point ABC. Now, in order to write this, I'm going to have to shrink it. So let P be this point in 3 space, A, B, C. Okay? That's a point on the surface given by alpha of x, y, z is equal to some constant k. And assume that the gradient vector of that function f lost it here. There it is not f sub p, yeah, at some point p, is not equal to the 0 vector. If it is, hang it up. You can't get very much out of that. So we're just assuming that the gradient is not the 0 vector. Then, if it's not the 0 vector, then this gradient vector f sub p is a vector normal to the tangent plane at the surface P, at the surface at the point P, is perpendicular to the tangent plane okay, at the point P. Okay? Moreover, the tangent plane to the surface is given by this formula. So this formula is that equation for a tangent plane. Okay? So, let's see if we can work a problem with that. Here's the problem. Find an equation of the tangent plane to this surface, and they don't write it down, so I'll have to write it down for you. 4x squared plus 9y squared minus z squared is equal to 16 at sorry point 213. Okay, at that point, 213. All right. Now, before we go any further, I like to always make sure the question makes sense. Okay? So if you plug in a 2 for the x here, that would give you 4, right? 4 times 4 is 16. Plus 1 for y would give you 1. So 9. 16 plus 9 is 25, right? Minus 9 would be 16. Sure enough, that's 16. All right. So that is a point that makes sense. Okay? That point does fit that. It's on the curve. All right. Now, let's just assume, and this is going to be hard sledding to do because I don't draw these things well. They don't give you the orientation of your axes, okay? Which is very unfortunate here. You know the z, the y coordinate is 3, so let's assume that this is the center, the origin down here. And so this point, how far you go from there to there, this is 3. I can't get that to connect. Something like that. This is z is equal to 3. Okay? Now, your x is a positive 2 and your y is a positive 1. So that means the positive x-axis is somewhere going back into the board here because you have to be coming positive on x2 and positive on y1. So if you have x, y, z, then the x must be back that way somewhere and y up this way a little bit. So 2, 1, 3. I can see the 3 part here. I can't see the orientation of the xy axis, but it must be twisted around so that you got a positive x and a positive y, not as positive as y. But you really don't need that, but just trying to get a visual of it. Okay. Now, find an equation of the tangent plane to the surface, that surface right there at P is equal to 0.16. P is equal to 213. Okay? We're looking for the equation of the tangent plane. Well, that equation of the tangent plane from what we just were given is f sub x at ABC x minus a. Think of that as your dx. Plus f sub y at ABC, and that's your y minus b, which would be not bad, plus f sub z at ABC times z minus c. And that's equal to 0. Okay, that's your equation of the tangent plane. All right, now, we know our ABC. 2 is A, 1 is B, 3 is C, so we can plug that in. But while we're there, before we get there, let's go on and take our f sub x. This is your f function, f of x, y, z. So let's do f sub x. What is it? Yeah, the partial of f with respect to x. Wait. You're taking the partial of this function here with respect to x.
Okay. So 8x.
8x. That's it, because you count those as constants, right? And you're doing with respect to x. So that would be 8x. Okay. Partial of f with respect to y would be 18y, and partial of f with respect to z would be negative 2z, right? Is that what you said? Okay. Negative 2z. Okay? Now you're going to evaluate this, each of these at your a, b, c. So let's do it. F of x is 8x, well your x is 2. So that would be 16 times x minus 2. So you're just plugging in, right? All right. Plus f sub y was, I believe that's 18y. I'm having trouble reading mine. But your y is 1, so that would be plus 18 times y minus 1. Okay. Partial of f with respect to z would be a minus 2z. Z is 3. So that would be a what? Second? Negative 6. Wait a minute. I don't know where that came from. Hey, I have no clue of where that came from. This is y minus 1, okay, minus 6 times z minus 3, and that's equal to 0. There's your equation of the tangent plane for that. Now, if you want to make it look a little neater, that'd be 16x minus 32 plus 18y minus 18 minus 6z plus 18 is equal to 0. All right. Goodness gracious. Yeah, my writing really stinks, but that's a plus 18. I was having trouble reading it. All right, so let's sort of combine things together. 16x plus 18y minus 6z is equal to, we'll move the 32 over and the 18 over, that would be plus 50. But subtract 18 from, that'll be plus 32, is equal to 32. So there is your tangent plane. 16x plus 18y minus 6z is equal to 32. That is the tangent plane at that point, right there. Okay, and they don't have axes, so I can't show it to you there, but it would be the one, the plane right here that this is perpendicular to. Okay? Now, one problem with this is a convex kind of surface there, and so your plane is actually on the inside of that, because on the outside rolling this way, but on the inside in that direction. So it's kind of a weird setup, but it's certainly doable. Okay. And that was the last illustration there. Do you want to do preliminary questions or not? Huh? Well, do you find them useful or? Okay, so let's do those. I don't think, yeah, that's the last slide. So let me remove all this ink from the slide. Okay, and let's do preliminary question 4.5 exercise preliminary question 1. Which of the following is a possible value for the gradient del f of a function f of xy for two variables, x and y, I assume. A, 5, B, 3, 4. Okay, that's angle bracket 3, 4. Or C, angle bracket 3, 4, 5. Which of those is a potential gradient of the function f of x, y in two variables, x and y? B, that's exactly correct. Because a gradient is a vector, that's a scalar, so it can't be A. Okay? A gradient in two variables has to be a two-component vector, that's B, it can't be C. So you're absolutely right, it's got to be B. Or at least I think you're absolutely right. Let's see what the back of the book thinks. This is 14.5, preliminary B, 3, 4. Perfect. Okay? Let's do number 2. This is a true-false. A differentiable function increases at the rate magnitude of delta f, of gradient f at P in the direction of delta LP, in direction of gradient FP. Okay? True or false? A differentiable function increases at the rate of its magnitude in the direction of the gradient itself. Okay. I'm okay with that pretty much, except that this thing here, the magnitude is always a positive number. And it's certainly, yeah, that's still okay. Because that's the maximum rate of increase. Yeah. I think I'm okay with that. I think true, unless, what do you think? True, false? True. Let's see what they say. 14.5. Nope. False. Okay. Let's see why. The gradient f of p points in the direction of maximum rate of increase. The maximum rate of increase is del f. Okay, what is wrong with the picture there? A differentiable function increases the rate of that in the direction of, seems like, I don't know if you have your book in front of you, but the summary, the 1, 2, 3, 4, 5, 6, 7th bullet down, and the very first dash under that first bullet seems like it says exactly what number 2 is saying. And I don't know why it's not, so let's just leave that one alone. Number 3, describe the two main geometric properties of the gradient del f. Two major geometric properties. Okay? Again, if you were to look up above, the basic geometric properties of that seventh bullet I was talking about of the gradient, as long as it's not the zero vector, is that the del F points in the direction of maximum rate of increase, and the maximum rate of increase is the magnitude of that, and that the minus that would be pointing in the maximum rate of decrease, and it would be the opposite of that, and that the del F at P is orthogonal to the level curve or surfaces at P. So there's actually three statements there. Okay, I'm guessing they want the first and the third maybe. Del F points in the direction of maximum rate of increase and is normal to the level curve. That's what they want. Number 4. You're standing at a point where the temperature gradient vector is pointing in the northeast direction. In which directions should you walk to avoid a change of temperature? So, your gradient of the temperature vector is in the northeast direction. Let's say that's north, that's east, so there's northeast. Okay? Now, which direction would you need to walk to avoid a change of temperature? Okay, no options, it just asks. Okay, so here's the deal. The gradient is in that direction to the northeast. That's the rate of maximum increase of temperature. That means maximum decrease of temperature would be south. Yeah, I can't remember what direction they said. Southwest. Okay, southwest, because this is northeast. Yeah, I was pointing northeast. So to get no change in temperature, you go this way because it's perpendicular or orthogonal to your level curve. And that would be either southeast or northwest. So either southeast or northwest. Those are your options, okay? But those are the answers. And let's see what they get. Either northwest or southeast. Wait a minute, they did give options. I'm sorry, I didn't even see this. The options were northeast, northwest, southeast, and southwest. I didn't read far enough to see that. Number 5. What is the rate of change of f of xy at 0, 0 in the direction making an angle of 45 degrees with the x-axis if, goodness gracious, my back for some reason is itching like someone put poison ivy down it. I don't know why, it's just suddenly itching. What is the rate of change of f at xy, f of xy at 0, 0, in the direction making an angle of 45 degrees with the x-axis if del f at 0, 0 is 4, 2. So that's first thing they give, that del f, the gradient of f at 4, 2, no, at 0, 0, is, that vector is 4, 2. Okay. Okay. Now, what is the rate of change of f 0, 0 in the direction making an angle of 45 degrees with the x-axis if del f at 0, 0 is 2. I'm sorry, I wrote it backwards. No wonder I was having trouble following it. That's 2, 4. Sorry. Okay. It's 2, 4. Okay. Now, this doesn't have any options on it. Let me look and see that. Okay, so that's del F. Okay? Now, basically, it's that little formula that we had. Ah, there it is. Well, I can't see it yet. They don't give it to you exactly, but, oh yeah, there they do. Oh, you don't have a book. Okay, sorry. If you look above in the summary, they have a bunch of bullets there. The 1, 2, 3, 4, 5, 6 bullet down, that's the one I think you'll need. Okay? And what it says there, it's what I thought I'd written above, but I haven't. Okay? Is this one. It's the directional derivative in direction of u, and it doesn't matter about u now, of f at AB, and your AB here is 0, 0. Okay? Is equal to the magnitude of the gradient of f at 0, 0 times the cosine of the angle theta. And they told you this was 45 degrees. Cosine 45 degrees. Okay? Well, all you have to do here is take the magnitude of this. And what is the magnitude? Is square root of what? Yeah, 4 plus 16 is 20. Square root of 20. So that will be root 20 times, what's cosine of 45? Second? Okay. So, I don't know why I'm itching so. So it's 0.7 times, I was just going to say root 2 over 2, okay, which is 0.7, okay, 0.717, something like that. Okay, but this root 20 is the square root of 4 times the square root of 5. Square root of 4 is 2, so the 2's go out, and that would just give you root 10. So see what root 10 is. Okay, and let's see if that's what they get. Oh, sorry, they don't do that. They just say, how did they get that? They get 3 root 2. I see the root 2 part, I get root 3. I mean, root 5, root 2, they get 3 root 2. And I don't know exactly how. So we'll leave that one off too. All right. Homework exercises here. Sorry, we need to move. Either 1 or 3 or both. 5 or 7 or both. Any of the odds 9 through 19. Any of the odds 21 to 29. Do 31 or 33 or both. Do 35. Any of the odds 37 through 43. Either 45 or 47 or both. 49 says you need a computer algebra system. If you don't have one, just sort of skip that. Take a look at it and see if you can figure out what they're talking about. then do any of the odds 51 through 63. All right. All right, that wraps up 14.5, finally. Let's move on to 14.6. Okay. Hopefully we'll get most of this one done today. Okay. All right, here we go. Why they have such a huge slide and such tiny print on it, I do not know. Okay, here, make it a little bit more easily read. So here we have a function, scalar function, f of x, y, z, but it's also a composite function because x is a function of s and t, y is a function of s and t, and z is a function of s and t. So this is a composite function of two independent variables, s and t, two intermediate function variables, x, y, and z. I say intermediate because they're functions each of s and t. They're not independent. They are of each other, but they're interdependent on the s and t. So ultimately your independent variables are s and t, and then the intermediate kind of variables are x, y, and z, and your function is operating on those. Okay? So that's what we've got. Says here, the chain rule for paths that we derived in the previous section can be extended to general composite functions. For example, suppose, for example, the x, y, and z are a differentiable function of s and t, like I show here, and that x is some function of s and t, y is some other function of x, s and t, and z is some function of s and t. We just don't know what they are. Then the composite function of those would be is a function of s and t, and we say the s and t are the independent variables. The others we sometimes will call intermediate variables. Okay. So here's example 1. Find the composite function where f of x, y, z is equal to xy plus z. Okay? And x is equal to s squared, y is equal to st, and z is equal to t squared. Okay. It says find the composite function. Okay. All right. So what we're looking for is f of s and t. No longer x, y, and z. So what we do, we plug in what x is. X is s squared. What is y? Say again? st. You see? st plus z, which is t squared. So your f of st is s cubed t plus t squared. All right. Yep, that's all there is to it. S cubed t plus t squared. All right. Now, if we were taking a derivative of that function, okay, The chain rule expresses the derivative of f with respect to the independent variables, and with respect to the other variables as well. Okay? Now, not just that function we did, but any of them. The partial of f with respect to s is going to be the partial, sorry, if I slow down my writing to match my talking, sometimes I get messed up. That would be the partial of f with respect to x times the partial of x with regard to with respect to s. Okay. I know that's hard to read. My writing stinks. Okay. Plus the partial of f with respect to y times the partial of y with respect to s. Plus, let's see, yeah, there's 3. Partial of f with respect to z of partial times the partial of z with respect to t. No, I'm sorry, s. I was jumping up and doing the next one. Whereas the partial of f with respect to t is partial of f with respect to x, partial of x with respect to t, plus partial of f with respect to y times partial of y with respect to t, plus the partial of f with respect to z times the partial of z with respect to t. Sorry. Goodness gracious, getting things to write straight. I'm having trouble. My eyes are going wacko on me. Okay. And that's our equations 2 and 3 at the bottom of page 687. Partial of f with respect to s, partial of f with respect to x, and partial of x with respect to z, s, and y, and z, and then partial of f with respect to t, or partial of f with respect to x, partial of x with respect to t, then y, then z. Okay. All right. Now, a couple things I want you to note here. Note that we can recover the formula partial of f with respect to x by labeling each edge. I think, okay, I didn't think about it, but here they had what I just written out for you, okay? But again, really small, okay? This is blown up. Partial of f with respect to s is partial of f with respect to x, and partial of x with respect to s, plus partial of f with respect to y times partial of y with respect to s, plus partial of f with respect to z times partial of z with respect to x. S, and then you do the same thing for the t's. And again, I just wrote this out, so you probably don't have to do it again, but if you find it useful, partial of f with respect to t will be the partial of f with respect to x, partial of x with respect to t, partial of f with respect to y, and partial of y with respect to t, partial of f with respect to z, partial of z with respect to t. Okay. Now, here is the figure they were doing. No, they're not. Okay. I was afraid of that. I couldn't remember that the new edition had this slide on it. Okay. No, the new edition has the figure, but the old edition didn't have this slide. And I'm going to, I know you don't have your book. Let's go back to this. Okay. Now, here's your F function. It's a function of x, y, and z. X and y and z are each a function of s and t. S here, s and t, s and t. So if you do the partial of alpha with respect to x, you here, partial of alpha with respect to y is here, partial of alpha with respect to z is there. This is, sorry, people at home, I'm not writing anything, so you're not seeing it. And then do the second layer, the partial of alpha with respect, the partial of x with respect to s RT, partial of y with respect to s RT, partial of z with respect to s or t. And you get each of these then at the bottom. And that's what the figure is supposed to show. Get your book and look at it. Hopefully you can follow what they're saying. You're starting with alpha at the top, going to the intermediate variables x, y, and z, and then going to the independent variables s and t at the bottom. And you follow the path that gets you there, okay? If you start at alpha, partial of alpha with respect to x, and then with respect to x with respect to s, that gets you down there. Partial of alpha with respect to y, partial of y with respect to s, that gets you down there, and partial alpha with respect to z and partial of z with respect to s, that gets you down there. So you can go either one of the two routes there. Okay. Now, they do some other manipulations here, and I'm trying to see how important these are. Can I kind of skip by them? Okay. Okay. Let's just jump to this. I think we've pretty much done all the intermediate steps. I was just trying to see if there was anything special in what they're doing in between what we just did and this step. It looks like it's all pretty much here. Here's the general version of the chain rule. So, in this case, we're not limited at x, y, and z. Alpha is a function of n intermediate variables, x1, x2, x3. Xn is a differentiable function in n variables. Suppose each of those variables, x1 through xn, is also a differentiable function of m independent variables, t1 through tm. No longer s and t, but t1 through tm. Then for T1, going from 1 to M, okay, let's just pick the kth one of these, any one of them, 1 to M, the kth one of those independent variables. Then the partial of alpha with respect to that t sub k is the partial of alpha with respect to your x1 times the partial of x1 with respect to that tk, plus partial of alpha with respect to x2 times x2, partial of x2 with respect to, and on. Notice your f goes to these functions, the partial with respect to each one, and then that function, then you take the partial of that function with respect to the tk that you're going for. Okay? So I don't think there was a huge jump between where we were and here. Really can't tell that much why they had the middle of the page occupied with stuff, but we'll maybe see it in a bit. Okay? Now, These are called the primary derivatives, the partial of f with respect to that intermediate variable. And then the specific partial of that variable with respect to the independent variable is then the second part of that. Okay? The term primary derivative is not standard. We use it in this section only to clarify the structure of the chain rule. So don't sweat that. All right. Now, let's see if there's another way we can write this. Okay? That's the general version. Here's another way to write that. Okay? The partial of f with respect to one of those independent variables, t sub k, is the partial of f with respect to x1, with respect to x2, with respect to x3. These are basically your gradients with respect to that, times the partial of x dotted with partial of x1 with respect to tk, partial of x2 with respect to tk, all the way up to that. Okay? And like I just inferred, that is just like your gradient vector in x, y, and z. Okay? And they don't show that here. So let me write it down here. They show it in the new edition, but not in the old. So this is another way of saying partial of f with respect to t sub k would be, and this is the gradient of f of x1, x2, x3, dot, 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 up to and including x sub I. Okay. I was trying to think. I'm trying to write as small as they do, and I'm just not doing a good job of it. N. Okay. That gradient dotted with then the partial of x1 with respect to t sub k, partial of x2 with respect to t sub k, comma, partial of x3 with respect to t sub k, comma, dot, 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 all the way up to and including partial of x sub n with respect to t sub k. For any one of, oops, that's a vector, not a scalar. Okay. All right. That just expresses it as a dot product. Okay. Let's do example 2. I don't think there's going to be a slide for this, so let's, yeah, I hit the wrong key again. Erase that ink. So, is this the same one we did before? Yeah, it is. I thought so. Let's go back to f being function of x, y, and z. And this will be xy plus z. And it says calculate the partial of f with respect to s, where x is equal to s squared. I think this is the same as before. Y is equal to st. And z is equal to t t squared. Okay, just bump that off before. Okay, same values we had before. Now, it says calculate partial of f with respect to s. Okay, can you tell me what that would be? Partial of f with respect to x times partial of x with respect to s plus y with times the partial of y with respect to s again plus partial of f with respect to z. Oh, Johnny come lately. Okay. Good to see you. All right, Treddy is here. All right, let me just refer back to what I said earlier, just so you'll have a chance to hear it too. I've gotten both of your papers in. The third person hasn't submitted a paper yet. I've only gotten one test one in, right? Okay. I need the other two. And maybe today I'm giving you test two if we can finish it in time. And then we'll spend most of the next time just talking generally about multiple integrations. We're doing multiple derivatives now. We'll do multiple integrations then. Okay. And I wanted to return to you your first test next time, but I don't have it in yet. So if you can get it to me, I'll get it back to you as soon as I can. Okay. So here was our situation here. What we were asked for is, this is example 2 on, well, you don't have the same book, but it's doing the chain rule with several variables. Okay? That's where you would look for it. So here's your function. F of x is equal to xy plus z, and x is s squared, y is st, and z is t squared. And it says calculate the partial of f with respect to s where that's the case. Okay? Well, we just wrote down with Jasmine's help what partial of f with respect to s was. Well, let's write down what the partial of f with respect to x is from here. What would that be? Huh? Partial of f with respect to x. Y. Perfect. Partial of f with respect to y. X. Partial of f with respect to z. 1. Perfect. Okay, partial, now these will be taken from this. Partial of, x with respect to s, that's what we're interested in here. That would be what? 2s. Partial of y with respect to s. T. And partial of z with respect to s.
You mean t, right?
Nope, s.
Oh, that's or just
0. If that's what you meant by nothing, 0, you're absolutely right. Okay? So now we plug in. The partial of f with respect to s is equal to y. Now we can write down what y is. That is st times the partial of x with respect to s, and that's 2s. So it's 2s squared t plus partial of f with respect to y is x. Well, x is s squared, so that would be a s squared times the partial of y with respect to s, t. Okay? And then the third one's pretty easy. That would be plus the partial of f with respect to z. Ooh, why did I leave that? Oh, I guess you came in right about that. Partial of z with respect to s. I forgot to write that down. Okay? And that would be partial of f with respect to z is 1 times partial of z with respect to s is 0. So that's nothing, as you said. So there's your partial of f with respect to s. Okay? Let's see if we can find where they got their answer. Yes. Ooh. Okay. Oh yeah, okay. And they just combine like terms then. Partial of f with respect to s would then be 2s squared t plus s squared t would be 3s squared t. I thought, where did they get with a 3 there? Well, they added 2 terms together. Okay. Now, if you went back to the first example we did, which was this very same formula, the function, and with all the sub-things, it said find the composite function, and I've already erased that, but what we had then was what we had before was f of this thing up here when you plugged in what these composites were. So you came out with f of st. What we got before was s cubed t plus t squared. Okay? Now, you weren't here when we did it, but here's what we did. X was s squared, y was st, that's s cubed t, plus z was t squared. So that's how we got this. Now, if we did the partial of this with respect to s, we would get, that's what we were just doing, partial of f with respect to s would be 3s squared t plus 0, right? Also partial of this with respect to s would be 0. And that's exactly what we got there. So you see 2 ways of doing it, either the composite function and doing that way or doing the chain rule. Either way. All right. That was example 2. All right. Let's see if we can do example 3. I don't think we have this on the slide either. So let's clear. I hit the wrong key again. All right. Here's a new function. This is only 2-dimensional, alpha of xy. And this is e to the xy. Okay? And it says evaluate the partial of f with respect to t, where, or at the point STU. Now they're doing something a little different this time, which is perfectly fine, is equal to 2, 3, negative 1. Okay, before we had 3 intermediate variables and 2 independent variables. Now we got 2 intermediate variables with 3 independent variables. Yeah, it still works. Yes. Just keep up with what you're doing. And they also are going to let us know that x is equal to st and y is equal to s minus ut squared. Okay, that's your secondary functions, I guess you would say. Okay? So we want to evaluate this at that point. So what is partial of f with respect to t? You tell me. Chain rule. Partial of f with respect to x times x with respect to t. Why will that not show? Okay. Okay. Plus y times to t. Exactly. We don't have to worry about the s and the u at all. We're only dealing with the t's here. Well, let's from here give what the partial with respect of f with respect to x is. We're doing this one first. What is that? E to the xy. But you got a little bit of a chain rule there. Times y. Perfectly. Perfect. And we also will need dx dt. We can get that right here. Partial of x with respect to t, that would be partial of x with respect to t from right here.
That would be s.
S. Okay. We also need the partial of f with respect to y for this piece. And what would that be? X times e to the xy. And we'll also need the partial of y with respect to t, which we would get here. Partial of y with respect to t would be
negative 2 ut.
Negative 2 what?
T.
Negative 2 ut.
Yeah.
U is counted as a constant. Did you say u?
Yeah.
Oh, okay. Maybe your 2u went together. Okay, right. Got it. All right. So now we can plug and chug and see what we get. Partial of f with respect to x is y e to the xy times s, right?
Yeah.
Plus x e to the xy times a negative 2 ut. But let's get everything into our independent variables because that's what we want to do. We evaluate it at those values. So your y is from here s minus ut squared e to the xy would be s squared t minus s u t cubed. Is that right? Okay. We're doing e to the xy. That's what I was doing there. Okay. So your xy, x times y would be s squared t minus st cubed u, right? Or s cubed t. Right?
Yeah.
All right. No. Okay. And get a little dicey, can it? Okay, that's the first part. Okay. Okay. That was my S. Yeah. That was the S minus UT squared e to the that, and then I'm going to multiply all this by S again. So that would be an S squared here and an S there. Okay. All right. I think I got that one done. Okay. Plus your X is ST times, and the e to the xy is the same as what it was before, which was this thing right here, right? E to the S squared T minus SUT cubed. Okay. But then you got to multiply that by, all this by, a minus 2UT. So that'll be, let me just, make that a minus 2UT squared times all that. I think that's right now. All right. So that's what it is. Now you do it at that point there. So that's your partial of alpha with respect to t, this thing right here, okay? And we plug it in at those values. So partial of alpha with respect to t at those values would be 4 s squared, there's 2 squared, that would be 4 minus 2 times a negative 1, that would be a plus 2 times 9, that would be a 18. I think that's a plus 18 now. E to the 4 times 3 is 12 minus, that's going to turn out being a plus because t cubed is going to be a minus 1, 6. Okay? All right. Minus 2u, which is going to be a plus 2. S is another 2. T squared is a 9. E to the, and that's still going to be 18, I believe. Okay. I'm trying to do it fast because we're running out of time. This will be 22 e to the 18 plus 4 times 9 is 36 e to the 18, which I think is 58 e to the 18. Can that be true? That seems like an enormous, enormous number. 58 e to the 66? Well, we got the 58 part right. Oh, maybe we didn't do all that. Okay, I'm trying to find it now. E to the xy okay. Oh my goodness. Yeah, that's where I messed up. When I multiply these two together, that should be, I thought I did it, s squared t minus SUT cubed. That's what I got. Well, did I make a mistake here then? That would be 4 times 3 is 6. I mean, 4 times 3 is 12. And then that would be a plus 6. Where did they get that? Okay. I think I just made a mistake here. I just don't see it. ST is 6. I see that, and S minus UT would be 2 plus 9 is 11. Why doesn't it work doing it the other way? Well, I see theirs is right. I don't see where I made my mistake, but we're out of time, way out of time. So sorry about that. If you can figure that out, it's got the 56.
Which one was it? What number?
That was example 3 on page 789. I can see where 6 times 11 is 66, but why doesn't that work to do it this way? If you multiply the letters first, ST times S, that would be S squared T minus SUT cubed. And when you plug those in, well, number 1, 4 times, no, that would be 12. Oh, no, I'm sorry. This is where I blew it. T, I got them crossed up. The U was minus 1, so yeah. And T was 3. T cubed is 27. So that's 2 times 27 is 54. Yeah, and that's 66. Yeah, I'm sorry. That's where it is. It's plus 54. Okay. So that would be 66. Okay. Okay, got it. I got my, because I put them in different orders here, I looked at the numbers wrong there. The U was minus 1 and the T was, yeah, that's where it was. Sorry about that, folks. Okay. We'll start next time with example 4. Let me give you a few homework exercises here. Do number 1, any of the odds 3 through 9, any of the odds 11 through 15. And we'll pick up the rest of those next time. All right. Okay. Oh, you want me to go and give it to you now? Okay. Let me make my mark here so I don't lose where we are, and put this into place so I don't lose that. And see, what I was thinking of doing was taking that test and just adding a couple problems from the next one and let that be the final. Okay? Okay, because we're not going to get much covered in chapter 15. We are going to go to that very soon next time. We're not doing 4.7 or 4.8, 14.7 or 14.8. We're going straight to 15, multiple integration, which is really not too bad. It's a pretty simple procedure, and we'll just go from there. So I'll just give you a couple more problems. But I could go on and give this and then just add the second problems later. So, huh? Okay, well, are you sure you don't want to get started a little earlier? Huh? Okay. Okay, I've just got to make sure. This is the trouble is I'm not absolutely.
So this is test 2 you're giving out?
What's that?
Is this test 2?
Yeah, this is test 2. This is what I want. Okay. Let me see if I have any copies done of it. I've only got, I got 2 copies of the first page and only 1 copy of the second page. I don't know how that came about. Okay. It may be that's my original. Somehow I wound up. So. Okay. If you want me to, let me run down and make. I need 3 copies of this, so it won't take me long to get it. Let me turn this off.